Hello everyone, welcome to this third lecture of this topic, Introduction to Finite Element and Method. This is Mr. Suyog Patil, working as Assistant Professor in Department of Mechanical Engineering, Sharad Institute of Technology, College of Engineering, Yadrao, Ichalkaranji. Okay. In this lecture, we will discuss the basics of this finite element method part 2, or again we can say in this lecture we are going to discuss this meshing required in this finite element and method, then field variables and the pre-processing or phases of this finite element and method. So first of all we will see what is meant by this meshing, or this why this meshing is required in finite element and method. Okay, so the basic idea of this finite element and analysis is to make calculations at only limited, or we can say the finite number of points, and then interpolate these results for a entire domain or the surface or the volume that we need to analyze. Okay, so therefore in this finite element analysis, as already we discussed, that this first step in this finite FEA is we have to divide this entire surface. We have to divide here this entire surface or this entire object into small number of pieces. Okay, that is called as discretization, and these small pieces are called as elements. Okay, so therefore we have to divide this object into a finite or limited number of the points. Okay, and then find out the results for these limited points and interpolate the results for the entire domain. Interpolate the results for the entire domain or the surface. Okay, then any continuous object has infinite degrees of freedom, and it's just not possible to solve the problems in this format. Okay, now when we see this is an example, okay, this is an object, it has infinite number of these points. Okay, infinite number of the points, and each point has a 6 degrees of freedom. Okay, here we can see the number of points are equals to infinite and degrees of freedom per point is equals to 6. Okay, so that means any continuous object has infinite degrees of freedom. So therefore this total degrees of freedom or total equation for this entire object is infinite. So, and it is not possible to solve the problem in this format. So therefore infinite equations will be there, as the total equations are infinite. So therefore it is very difficult to solve this problem. Okay, then therefore finite element method reduces this degree of freedom from infinite to finite. Okay, with the help of this discretization or meshing. So therefore here we can say, see, this number of nodes is equals to 8. That means this first, second, third, fourth, fifth, sixth, seventh and 8 by using this 8 number of nodes and 4 elements, this object is discretized. Okay, or this is divided into 4 species, small pieces. So therefore number of nodes is equals to 6, and degrees of freedom per node, degrees of freedom or at all the nodes is equals to 6. So therefore this total equations is equals to number of freedom, degrees of freedom into number of nodes. Okay, so therefore 8 into 6, 48. Okay, total equations for this area is 48, and here in this area, without using this finite element and analysis method, this total equations will be infinite. Okay, so therefore this finite element method reduces these degrees of freedom from infinite to finite, and which helps the solving these problems, real life problems. Okay, one more another aspect of this meshing is the accuracy of your solution. Okay, so accuracy of the solution depends on this again meshing, as we seen in the previous lecture. uh, the size of this element is, if the size of this element is small, okay, so or we can say the fine meshing or small meshing is there. Okay, so in that case the accuracy increases. So therefore this accuracy, again from this accuracy point of view, so we should mesh this object or mesh all the objects very smoothly, or fine meshing is required. Then here we can see again, we need to be able to use meshes that smoothly change in the size. Okay, that means here we need to be able to use the meshes that smoothly change in the size near the boundary where we expect the solution to change a lot. Okay, so that means here this size or shape is changing, that means a sharp corner is there here. So here this fine mesh should be there. Okay, we should use this mesh fine here, or at this boundary edges this meshing should be fine. Okay, compared to this other or this object on the center point. Okay, so because this solution is may change at this edges, sharp edges, or at this boundary edges. Okay, so therefore this meshing should be fine at this boundary surface or at the corners. Then also here we can see when there is a when we need the mesh to be able to get small near the sensitive spots. Here the sensitive spots is there, here it is this line is there, here this graph is there, line is there. Okay, so at this line or at this point, sensitive points, this meshing should be small. Okay, or fine meshing should be there, or element size should be as small as possible. Okay, so this is the meshing requirement in this FEA. Then again here we can see we need to be able to place a mesh on a surface that includes holes and edges. Okay, now here we can see this is an case 3D object. Okay, where this object has a some holes. Okay, and surfaces. Okay, so therefore our sharp edges are also there. Okay, so therefore in such applications or such cases, this meshing should be done properly. Okay, fine meshing should be done at the edges. Then again here we can see the mesh must be able to adapt to local features. In this 3D case, this curvature is the local feature. Okay, or we can see here in this object, in this 3D model, we must mesh this object smoothly. So therefore this meshing should follow a 3D features, or it adopts this local feature, that is curvature shape. Okay, this curvature, this, or again here we can say this is the curvature shape. Okay, so this meshing should adopt this 3D feature. So therefore in such a real life problems, or this in such a complex problem, manually this meshing is very difficult. Okay, so therefore, and this meshing should change, or this meshing should be smaller in the corners or in the hole whenever there is holes or edges. So therefore it is very difficult to mesh manually. And so therefore nowadays some of the CAD packages, software packages are available. Okay, in that this meshing can be done very easily. Then we will see types of these meshes. Okay, so there are generally three types of these meshes: solid mesh, shell mesh, and beam mesh, or again we can say 3D element, 2D element, and for 1D elements. So in this solid mesh, the program creates a solid mesh with tetrahedral 3D solid element. Okay, tetrahedral 3D solid element is used in this solid mesh, and the tetrahedral elements are suitable for bulky objects. Okay, in the solid objects, or we can see here in the solid object or the bulky objects, these tetrahedron solid elements are used for this meshing. Then similarly for this shell mesh is used when this sheet metal or uniform thickness objects are there. Okay, or surface geometry is there, uniform thickness and this sheet metal surface geometry is there. In such a cases this program automatically creates a shell mesh. Okay, here we can see this 2D sheet metal object is there, and here 2D elements are used for this meshing. Okay, then beam mesh, then this program automatically again uses this beam mesh and identifies the joints for touching or interfering structural members and non-touching structural members within a certain distance. So therefore this number of 1D beam elements are used to connect to each other, and this meshing can be done in one dimensional or 1D element by using 1D elements as also. Then how to start meshing, or some of these basic rules while meshing these objects. Okay, so first of all we have to spend some sufficient amount of time, okay, for studying this geometry. Okay, this studying this in this real life complex engineering problems, we must spend some time to study the geometry, the shape of the component. Okay, or some other geometrical entities in the present in the geometry. Okay, that we have to check. Then we have to check the geometry for some of these points, like free edges are there, whether the free edges are present in that, scar lines are present or not, then duplicate surfaces, small fillets or small holes are present in the objects. Okay, beads or intersection of the parts or assembly components are present in the geometry. Okay, so therefore we have to check this geometry, or we have to check this number of parts in the component. Okay, then after that, time estimation, time required, we have to calculate the time required for this meshing and for this analysis. Okay, as this meshing is very small, this element size is very small. Okay, we will get accurate result, and it increases the time, or this consumes the time. Okay, time for the analysis. So therefore this time estimation should be there again. Okay, then again we have to check the symmetry of the object. Okay, so suppose this is an object, a square plate having a hole at the center. Okay, and that we have to assume here, we have to analyze here. Okay, so therefore we have to consider a meshing only on a quarter of the plate. Okay, so therefore this first quarter, we will consider this first quarter. Okay, here, so we will take this much of this object and we will mesh on this object, meshing only a quarter of the plate, and reflecting it twice is advisable. Okay, mesh this object only and reflect it twice, that is one horizontal and one vertical. Okay, so that we will get this entire surface or entire object. Okay, meshing of this entire object. Then okay, so we have to check this symmetry of the object. Then again we have to check for this subpart symmetry and repetition of the features. Here in this figure we can see these holes are repeated at certain distance. Okay, this again these elliptical surfaces, these circles. Okay, these entities are again repeated here. Okay, so therefore we have to mesh this small piece of this object. Okay, we have to, when we mesh this, and we can copy and paste, or we can apply to all this entire surface or entire object. Okay, so therefore we have to check this repetition of the features and subpart symmetry in the problem as well as. Okay, so therefore we have to well, before starting this meshing, so we have to check all these points. Then selection of the type of the elements. Okay, this again selection of the type of the elements in meshing is very much important, because this in the real life problems we rarely use one type of the elements only. Okay, so we have to use, usually we have to use in real life problems a number of elements, that is 1D, 2D and 3D and some other elements as well as. Okay, so here we can see use of this combination of the element is required. Here the real life problem is shown. Okay, whenever we are going to analyze this bucket. Okay, so then in this the handle should be modeled by a beam element. This handle should be modeled. Here we can see this handle is modeled by beam element. Okay, matter 1D element. Then this bucket surface or this bucket body surface should be uses a shell or 2D elements. Okay, so this bucket surface body surface can be modeled by using shell or 2D elements. Then this, the connection between the handle and the bucket body through a rigid elements. Then again rigid elements are used to model this connection between this handle and the bucket. Okay, so here it is shown, this rigid elements are also used here. Okay, so that means this combination of this 1D, 2D and these rigid elements are used in this meshing of this object. Okay, so therefore in real life object we have to select different types of this elements for this meshing. Then type of the meshing. Okay, this type of the meshing is again depends on this. It is two types in the meshing. One, it is called a geometry based meshing, and second one it is called as FE or finite based meshing. We will see detail in next slide. Then again, in case of this joint modeling, some special instructions for bolted joints are provided while meshing this meshing any object where these bolted joints are present. Some special instructions are provided that we have to follow this while meshing this object. Then in spot and arc welding as well as some instructions are provided. Then at the adhesive joint, Okay, whenever there is a joint, adhesive joints are there in the real life problems or in the engineering complex problems, so we have to follow some guidelines related with this meshing. Then meshing in critical areas. Okay, in critical areas or in critical problems, this meshing, some of the meshing rules are there that we have to follow. In this first case, this is automatically meshed. Okay, automatically meshed composite component, where in this meshing is done by considering these abrupt changes or holes in this object and this change in the shape of this object. Okay, by considering this meshing is done here. Okay, and it is not properly done, so therefore this is not acceptable. Okay, and again we can say this meshing should be in a mapped mesh. Okay, so therefore this meshing should follow this object. Okay, this pictures, so that means this, it should be a straight line or it should be in a proper way. Okay, and whenever there is a hole, in that case, in that phase only we have to change this meshing. Okay, or fine meshing should be there in the holes or any other change in the size only. Then again here we can say in this hole, whenever there is a circular hole, minimum 12 elements around this hole should be there. Okay, while meshing any object, and is if there is circular hole is present in the object, so minimum 12 number of elements should be there around this hole. And if the square or hexagonal hole is there, then 4 to 6 elements should be there. Okay, 4 to 6 elements should be there, and generally is these rules are followed in this meshing. Then when there is a small fillet, okay, when there is a small filament, minimum 3 elements on the fillet should be there. Okay, this is the first row of the element, second and third row of this element. Okay, so minimum 3 elements should be there on the small fillet surfaces. Okay, but when there is a sharp corner or a large fillet radius is there, so therefore only one element can be used for the large fillets. Okay, for this fillet surface, one element can be used for this large fillet surfaces. Okay, so these are the some guidelines in the meshing in the critical areas. Okay, now after discussing this meshing, now nodal displacement. Okay, so there is some displacements and at these nodes. So nodes will have nodal vector displacements or degrees of freedom, which may include translation, rotation, and other special applications, higher order derivatives of these displacements as well as. Okay, so here we can say these nodes will translate, or sometimes it may rotate as well as. Okay, so that displacements of these nodes should be noted. Okay, that is called as nodal displacement vector. Okay, then when the nodes displace, they will drag the elements along in a certain manner dictated by this element formulation. Okay, so when these nodes displaces or this translates to one point to another point, these elements also may translate and element formulation will be there. Okay, deconstruction of this element is shown here in this figure, so we can see here this displacements of this nodes. Then one more important term in this finite element and method is the phases in the FEM or finite element and method. Okay, the phases of this FEM, there are main three phases. One, it is called as preprocessor. Second, it is called as solution or processor or processing phase, and third one, it is post processor or post processing phase. Okay, in this first phase, pre-processing phase, the analyst develops a finite element mesh to divide the given geometry. Okay, the analyst must divide the given geometry and divide this finite element mesh and applies the material properties and boundary conditions in this pre-processing stage. Okay, in the first phase, this analyst must provide this or apply this material properties and boundary conditions and meshing of the object. Then in the second phase of this FEM solution phase, during which the program derives the governing matrix equations from the model and solves for the primary quantities. Okay, so that means after meshing all these elements, this program derives these governing matrix equations for this shape function and solves these matrix equations for this primary quantities that we need to calculate. in this solution phase or in the processing phase. And in the third phase, that is post processing phase, analyst checks the validity of the solution. Okay, examines the values of the primary quantities such as displacement, trace. Okay, and derives some additional quantities as well, as for example buckling load, then pre-damping vibrations. Okay, node the frequencies, damping frequency of this objects. Okay, such additional values that we need to calculate. Okay, so that can be calculated in the third phase, that is in post processing phase. Okay, so we will discuss in detail in this pre-processing stage. The goals of the pre-processing are to develop an approximate finite element mesh, okay, and assign some suitable material properties and apply boundary conditions in the form of this restraints or loads. Okay, the boundary conditions are in the form of these restraints, constraints, and loads that need to apply. Okay, so in this pre-processing stage, it creates and discretizes the solution domain into a finite element. Okay, first of all, this object is divided into number of small elements, finite elements, and that is subdivide the problem into nodes and elements. Okay, I think this nodes different 1D, 2D, and 3D elements. This object is divided into number of finite elements. Then next, assume a shape function to represent the physical behavior of an element. Okay, that is an approximate continuous function is assumed to represent the solution of an element. Okay, so therefore the shape function for all these elements are assumed here, and this approximate continuous function is assumed, and it is used to represent the solution of the object. Okay, by interpreting the results of these elements, we can estimate the results for the entire object. Then develop an equations for the element. Okay, it's separate equations for all the elements are developed in the pre-processing stage phase. Then assemble the elements to represent the entire problem. Okay, construct a global stiffness matrix. By assembling all these elemental equations, we must prepare a global stiffness matrix. Okay, or global matrix for this entire problem. Then apply boundary conditions and initial conditions and loading. Okay, boundary conditions, that means loading, different types of the loads. Then again constraints, some constraint that is fixed or cantilever type of the beam. So that again we have to apply this boundary conditions in the pre-processing phase only. Okay, then next second phase, it is solution phase, or sometimes it is called as processing phase as well. As okay, in this phase, this we solve a set of linear and non-linear algebraic equations simultaneously. Okay, to obtain nodal results, such as the displacement values at different nodes or temperature values at different nodes in a heat transfer problem. In case of this solid mechanical problems, we have to calculate the displacement, stress, strain values. Okay, so therefore we have to solve these algebraic equations. Okay, and we will get these primary results in case of the solid mechanics. And in case of this thermal analysis problem, we will get the different temperature values at the different nodes in the problem, heat transfer problem. Okay, in this second phase, processing phase. But in third phase, post processing phase, after a finite element model has been prepared and checked, boundary conditions have been applied, and the model has been solved, it is time to investigate the results of this analysis. Okay, and this activity is known as the post processing phase of this finite element and method. After pre-processing and this solution phase, the next step is, it is the post processing step. Okay, and we obtain the other important information here. In the post processing phase, we will get the other important information. For example, additional informations that we want to estimate or we want to know. Okay, so that we will get here in the post processing phase. Then at this point again, you may be interested in the values of this principal stresses, then heat fluxes, strains, etc. Okay, so that we can calculate in the post processing phase, in the third phase of this finite element and analysis. This is the third phase of this FEA. Friends, thanks for watching this video. If you like this video, please share, comment, and like this video. Then subscribe to my YouTube channel and click on the bell icon to get notified for more videos on this CAD/CAM subject. And thanks for watching. Thank you so much.